right, awesome. Um, so I put a little bit of a PowerPoint together. Hopefully this demonstrates a little bit of the idea behind some of what counterweights are. Um, Part of the reason why I wanted to talk about counterweight systems is some of you guys may know that I was in a pretty serious cave accident where I uh, had a fractured T4 and T5 vertebrae and a broken left ankle after I was stuck in a rock fall. My fellow cavers actually hauled me out of a 165-foot deep pit using a climbing counterweight system. And we'll go into why that system works and why we particularly chose that one for as the solution for what we were for the situation that we were in, and why that one, you know, um, worked for the resources that we had. But I just give a little bit of a preface of why this might be useful and why we care about that. So the general concept of counterweighting is it's different than it's not technically considered a haul system. Really, all we're doing is we're balancing um, a person balancing the rope over a pulley. So the concept is literally just rope over pulley. And if you guys can see my mouse, orange character is the patient in all of my diagrams, and green character is the rescuer in all of my diagrams. So the concept behind having a counterweight is this pulley here basically just has a rope going over it. And the weight of the rescuer is helping offset the weight of the patient. What's really happening here is you've really just got a change in direction of the rope. There's no technical mechanical advantage that's actually happening here. Um, so really, if you kind of think about a balance, if these two people weighed exactly the same, they're not going to go anywhere. If green person weighs more than orange person, green person's going to pull the weight down, and orange person would be coming up in this. Is really the main concept of that. So, um, when we use this to the advantage of hauling a person back up, um, we basically would be attaching the orange person to the bottom of this rope, and the rescuer would be on the other side of it. It's really quite simple. So we are not building any like 3-to-1s. We're not building any 4-to-1s or anything like that. We're just balancing weights over a pulley using a rope. So this is actually a very, very simple concept, but basically the reason why it's not necessarily used more frequently is it requires a very bomb-proof anchor. So this anchor needs to be very, very solid because there's going to be more weight that is put onto that. So in this particular instance, you've got orange person's weight and green person's weight. So now we have a 2-person load on that one anchor. As we get into other iterations of the counterweight system, this can actually turn into a 3-person load or more that is all built onto this one anchor. So this anchor has to be very, very solid. The other reason why we don't necessarily see this that frequently is it has to be ideally over a free hang. So if there's any sort of friction or rubbing of the rope, that could be a problem for this system as we've built it here. We want this to hang very freely. And so a free drop pit, similar to the one that you see me getting hauled out of here, is actually sort of an ideal situation for that because that rope is not, rubbing against that wall of the cave here. And actually where we had hung it was below the lip of the cave. So it wasn't dragging over any sharp edges. So the other thing we also need to be cautious of is any sort of rock fall. So the pitch needs to be clear because as this person is coming up and this person is maybe coming down or going up as well, um, we would potentially kick things loose on that wall. And as you can see, this person is in very, very close proximity to the rescuer. And the rescuer could easily just kick things down onto the patient as well. Or if the patient were to like bump up against the wall or something, they could be dropping things as well. So I also noted in this diagram, this is an incomplete system. It's just the illustration of having a rope over a pulley. This doesn't actually show the full fully built system of how you would pull this patient up. But there are three different types of counterweight systems, and I'm going to talk through each of the three of these. So there's a diminishing loop, a rappelling counterweight, and a climbing counterweight. And these three systems are all built differently, but they're all based on that idea of rope over pulley and rescuer's weight being used to help bring the patient up. So in the diminishing loop, it's called a diminishing loop because we're going to create a loop out of the rope. Something to note, is that this rope that we're going to use for this needs to be at least double the length of the pitch. And often we actually want it to be 4 or 5 feet longer than double the whole pitch. And the reason why is that this system is going to be built at the top. Perhaps the rescuer built it before coming back down and helping the patient, or perhaps somebody up top was able to build it and then drop the ropes down to both the rescuer and the patient. But what's going to happen here is both ends need to reach the bottom. The rescuer will basically attach the patient to one end of the rope using a butterfly knot, and then they will take the actual end of the rope and attach that to them on their seat harness. So on the D-ring of the seat harness, we've attached the patient using a butterfly knot about 3 or 4 feet from the end of the rope. And then we've used a figure 8 at the end of the rope to attach it to the rescuer. What that's done is now it's closed this system and has technically turned this one into a 2-to-1 mechanical advantage system. So generally, you only need one rescuer for the diminishing loop. And that is helpful because then you don't necessarily need to have more human power in this system other than just one rescuer, because you do have that 2-to-1 mechanical advantage. Now, when we call it a diminishing loop, the reason why it's a diminishing loop is that we've closed this circuit here by having the rescuer and the patient attached, and then that rope going over. The rescuer will be climbing the other end of that rope, and as they climb, the loop basically starts to shorten because the rope is being pulled up and over the pulley and out of the system. So what we've done is this rescuer is climbing this, and basically they're hauling this patient up through over the pulley. So one thing to note is this can be very, very energy intensive. If the patient weighs less than the rescuer will climb what feels like less weight than normal. But if the rescuer weighs less than the patient, the rescuer is climbing more weight than they're used to climbing. So they're climbing, like if this person was 140 pounds, and this person was 180 pounds, the green person is used to frogging themselves at 140 pounds, but now they're going to feel the weight of that patient as well. So they're going to feel 180 pounds instead, because it's balanced them out over this. Um, and this actually becomes very apparent when you're climbing. Um, the patient will tend to sink if they are on way more than the rescuer. But if they weigh less than the rescuer, they'll probably float around here, and this rescuer will be very busy climbing this rope, but the patient will be like floated above them effectively. Um, One thing to note is that this pulley, we have no progress capture on it. So basically they literally are just a little seesaw here. And then the rescuer, the advantage of this diminishing loop is that the rescuer is close to the patient the whole time. So depending on the person's injury, this may be an advantage to be using this system because perhaps this rescuer needs to manage some sort of an injury where they're trying to prevent this patient from like smacking into the wall or something like that, or bending weird or something like that. So that is how the diminishing loop is built. It is just a pulley with a rope that is longer than double the pitch. Um, and the patient and the rescuer are attached. I do have a note here that you could connect your cow's tails between the patient and the rescuer. But if you did get into a situation where you needed to pass something, or perhaps you get to the top and you want to attach this patient to the final haul system and then yank the whole system over, which I'll talk about that later as well. Um, that cow's tail may be needed. So it is a disadvantage to use your own personal gear for things like that. And if you have the rope to do it, you would use the rope if you can. Now, this system requires a lot of rope, and it's not very frequent that cavers are going somewhere with more than twice the rope of the distance that they want to rappel. So that is one disadvantage that we might have with this system, is that it's very infrequent that we've got enough material to pull this one off. But like we said earlier, with it being a 2-to-1 system, it is feasible because the rescuer has some mechanical advantage here where they can climb a heavier person up to the top, and um, because the rescuer can stay with the patient the whole time, that can be an advantage as well. Are there any questions on the diminishing loop? Okay. So I'm going to move to the next system, which is a rappelling counterweight. And the way that the rappelling counterweight works, before I get into that, actually, I'll tell a story. The rappelling counterweight actually is a really interesting system because it was used. It's very, very fast. This is a very fast system to bring somebody up. And if you look in the old ACA reports, the American Caving Accident reports, there was an injury where somebody was doing a through trip in Ellison's Cave in Alabama, sorry, in Georgia. And Ellison's Cave has the 2 deepest pits in the US. It's fantastic and incredible. And partway through that cave trip, there was a person who had a fall and had an injury. And basically, now you're faced with some very, very deep pits to try to get the person back up. This person actually had a few blood transfusions in cave because his injuries were that serious. But basically, they had to get him back up fantastic, which is nearly 600 feet deep, single pitch. So the way that they built the system was they decided to use a rappelling counterweight because he didn't have a lot of time, especially as somebody who was bleeding out. They needed to get him up fast. So um, the responding rescuers built the system, and I'll get to the end of the story, I guess, after I explain how this is built. Um, so here in the rappelling counterweight system, you're going to have to build two anchors instead of just the one that we were looking at earlier with the diminishing loop. So we have the bomb-proof anchor here with the pulley, and the rope goes over the pulley. Now, one of the advantages here is that this rope that's going over the pulley does not need to be um, exactly double the length of the pit. It can be shorter than that because your rescuer will start at the top instead of starting at the bottom. What the rescuer is going to do, so basically the patient will be attached to the bottom of the rope from the bottom of the cave, right? Um, and what I have here is a prusik. So I've got progress capture on this pulley, and the progress capture is only on the patient's side. What that's doing is that as this patient is coming up, we don't want a seesaw motion. We want the progress to be captured. So basically, as these rescuers are pulling the rope over that pulley, the rope cannot back out. So the patient cannot go back down because of this progress capture right here. So the patient is going to be coming up, and basically the way that this starts is the rescuer will be at the top, and they're going to attach the other end of the rope to themselves, and then they're going to rappel on a separate line, and we want this separate line to actually reach the bottom of the cave, because that's that's where these guys are going, right? So they're going to rappel down, and effectively what they're doing is they're pulling the rope that is over the pulley with them by using their weight to rappel this other line. Does that sort of make sense to everybody? So the patient is coming up because of the weight of the rescuer, but sometimes the rescuer doesn't weigh enough, right? So say we had a 200-pound person who got injured at the bottom of the cave here, and it's me who's about 140 pounds, trying to rescue them. Well, I don't outweigh them. So even if I started rappelling this, it's not going to move because I don't outweigh that person. And then there's also friction to consider. But if you took two 140-pound people, now we weigh 280 pounds. We now outweigh the other person. And basically, we'll rappel together, attached to each other. So the second person in this diagram is just attached to the rappeller, and the rappeller is rappelling this line, and this person is just serving like a sack of potatoes as extra weight. And as they rappel this other line, they are able to now pull this rope down and pull this patient up. So to kind of conclude that Ellison's story, the rescuer in that particular case was Elliot Stahl, an Indiana caver, who just so happened to be down there in tag. And they didn't have another person who wanted to be the sack of potatoes, but they did have some hungry cavers at the bottom of the cave who had been helping rescue this patient throughout that night. And so what they did was they actually filled up a sack, like a big cave pack, with a bunch of food and a bunch of hot coffee, with basically all of these provisions for all the rescuers. And that was the extra weight that they used to help bring the patient up. And I think if you look up that report, the time may actually be listed of how quickly they got the patient to the top from start of rappel. So basically, they had the person rappel this separate line with all of that food, and they were able to bring the patient up to the top. Now, the rescuer is going to control the rate of bringing the patient up by using basically that rappel device. If they were using a rack, for instance, they could squeeze their bars together and they would um, descend a little bit slower. They could spread their bars and rappel a little bit faster if that's what was needed. Um, so the thing to note here is that versus the diminishing loop, this system requires a little bit of extra gear. So we've got a progress capture on that pulley. We've got that additional anchor, and then we've got that rappel line that also needs to reach the ground. And then because this person may not outweigh this person very well, we're going to need some extra weight to help pull that rappel down. Are there any questions on the rappelling counterweight? Okay. If not, I'm going to move on to the next system, which is the climbing counterweight. So the climbing counterweight is built very, very similarly to the way that the rappelling counterweight is, in that we've got that bomb-proof anchor with the pulley. We've got that progress capture, which I've drawn as a ProSic on this system, but if you wanted to use like a microtraction, again, you could use like another pulley with progress capture type system. But in this case, I've drawn a pulley with a ProSic. And again, similar to that rappelling counterweight system, the progress captures on the patient's side only because as we're pulling that rope through, we don't want to lose the patient. So we're going to capture all that progress through that progress capture right there. There does need to be another anchor and another line. And basically what we're going to be doing this time is instead of rappelling this other line and dragging the rope through the pulley, we're going to have the rescuer get on the opposite side from the patient and they're going to start climbing that rope. And as they climb, it's basically pulling the rope over that pulley and feeding that rope through. So if the patient weighs less than the rescuer ends up feeling less weight than they normally climb. So say the rescuer is 200 pounds and the patient is me, and weighs about 140 pounds. Then this person outweighs me and they're going to have a good time kind of climbing because their weight offsets mine very easily. And then they're climbing a lot less weight. But if the rescuer is me and they weigh 140 pounds and the patient weighs 200 pounds, now the rescuer is trying to climb a lot more weight than they normally weigh. So in this case, we also don't have the mechanical advantage of the 2-to-1 that a diminishing loop is. What we're going to do is we're going to add another climber. So now we've got two people, and then they will together outweigh that patient, and they can use their strength both to climb rope through, pull it over that pulley. So this is more weight and more pull force by having those two people there. Now, we have to emphasize the anchor strength then, because as you can see, all three people are on this one anchor. So one of the major things to check when building any of these systems and any system in general is that your anchor is strong enough to withstand all the forces that you're going to be putting on it. Now, this other line that I've drawn here with this other anchor is because of the fact that we only have progress capture on the patient's side. So if for whatever reason, the patient were to unweight the system, say they got to the top and now they're at the lip and they stand up, or maybe they got to an edge somewhere in the cave and they stood up on the edge. that unweights the system. And because there's no progress capture on the rescuer side, there's only progress capture on the patient's side. What that means is that the weight of the rescuers would mean that this rope could come through that pulley, and the rescuers could go down because of that unweighting of the system. So what we want to do is we want to make sure that these rescuers are safe. This line here is basically a safety line, and these rescuers will have an attachment system to that rope. The way that this may happen is through maybe like a QAS. If they have a QAS on their harness system, on their frog system, maybe they have to manage that as they're climbing the main rope. They have to manage their QAS on this rope as just another tagline. Another way that it can also be done is once the system is balanced, these climbers will not actually be moving up this rope. What they're going to be doing is being pretty stationary, and because the system's at equilibrium, the they're basically climbing the rope in order to just pull it over the pulley. So they're going to be pretty stationary when they've reached an equilibrium. And what they can do is tie like a butterfly knot inside this rope, this safety line here, and clip a short cow's tail into it if they didn't have a QAS. So those are options for making this system work. So again, we're going to emphasize anchor strength for all of this. We're going to emphasize that it also needs additional gear, similar to how that rappelling counterweight had additional gear, where we've got a progress capture on that pulley now. And then we've got that additional anchor and this fixed line here for those rescuers. Now, one of the beauties of this system is similar to the rappelling counterweight. We don't need this rope to reach the ground on both sides. We need it to reach the ground on one side to reach the patient. But if this rope just goes over the pulley and doesn't necessarily reach the ground, because the rescuers are starting up at the top and they're going to be pulling that rope through, they can start with a less than terminated, like less than hitting the ground sort of piece of rope. The other thing is, because they're not rappelling down to the bottom of the cave in this case, this fixed line also can be a little bit shorter as long as it's within the place where these rescuers will have reached equilibrium with climbing. So basically this rope also does not necessarily need to reach the ground. It would be better if it did, but effectively, because the system just needs to make it over the pulley, basically you don't have to have it reach the ground either. So if you're short on rope, this could be an option. Now, one thing that I want to highlight is that we talked about how these counterweight systems are really good for a free hanging pit. And if the rope is able to hang without rubbing against an edge or something like that, that would be the best place where you can use these counterweight systems. However, most caves have some form of an edge. So in the case where you can hang the counterweight system under that edge and you can bring the person up to where that pulley is, effectively, once this person is up at the top, and they've reached where this pulley is, you can take their cow's tail and clip them into that anchor carabiner. From there, how do we get them over the edge, right? So that's the big problem, is how do we get them over the edge? And most caves have some form of a lip that you have to get over to finally get out of the pit. Well, the edge transition problem can be solved using something called a dragon haul. And it's called a dragon because you drag on. And so really what the dragon system is the place, this is a 3-to-1 built with a change in direction. So all this is this pulley here is a change in direction. Um, and what we're doing is uh, the position where this load is shown is where you would start building your counterweight system from. And then this change in direction rope, we would have it hanging next to that counterweight system. Effectively, once the patient is up to where that big carabiner was for that anchor, this whole thing is serving as the anchor now, and this rope would be hanging next to that counterweight system. We would attach the patient securely onto that carabiner, and the rescuer can transition off of the counterweight system itself and onto this rope, which is hanging next to this is the dragon. They're going to transition onto the tail of the dragon, and they can start counterweight climbing on this system to pull the person over the edge. So effectively, all it is it's a 3-to-1 system with a change in direction where the climber is moving from the counterweight system and transfers themselves onto the 3-to-1. And they climb on the haul rope of the 3-to-1 to drag the person over the edge. And this is going to have a lot of friction, but it pulls basically the whole system up and over. So it's a stacked haul system. Did that make sense to everybody, or anybody have any questions? All right. So I'm going to move on to the slide, which is about some of the pros and cons of each system. So the diminishing loop, some of the pros of that, we said, the rescuer and the patient are close together the entire time. There's no progress capture that's required, and technically there's mechanical advantage in the system as well. A few of the cons of that system, maybe we need more rope because of that, because we need a rope that is more than double the length of the pitch. And the rescuer starts at the bottom. The system's got to be built in place at the top, but the rescuer is starting at the bottom. So you have to have potentially more people or a way for that rescuer to get back to the bottom to start helping that patient. On the rappelling counterweight, a few of the pros. So it's fast. It's a real quick way to get the patient up. It was used in that Ellison's rescue. The rescuer can rig the system at the top and then start the descent. So they're all together up there. But some of the cons, we need to be in control of our rappel. It needs that second rope to rappel down that will actually reach the bottom. So not only did you need a super long rope in the first place, you need 2 super long ropes. And then the rescuer is at the bottom when the patient makes it to the top. So it becomes an edge problem for the patient. And you might want to have a couple people at the top to help that patient get over the edge of the lip. For the climbing counterweight, some of the pros, it's controlled pace for bringing the patient up. The rescuer can rig the system at the top and then start the haul. And then the rescuer is at the top when the patient is at the top, and then they can help them with the edge transition. Some of the cons of it, though, is that the rescuer must also be able to transfer onto that separate line as the patient unweights the system. So that fixed line is there because there's progress capture only on the patient side. And if the patient were to unweight the system, the rescuer's weight would pull them down to the bottom of the cave. And then the ride coming up on a climbing counterweight can be kind of jerky because the rescuer is climbing on the other side. So depending on the pace of the rescuer and their climb, that can cause some jerking in the system. Any questions about this table? Okay. So back to my particular cave accident. I was not in a place where I could climb out of the cave on my own at that point because I did have a mechanism of spinal injury. We didn't know what was wrong with me yet at that point, but we did know that I had been hit pretty hard by a very big rock. Um, so I was not in a place where I could successfully climb out of this cave. Um, some of some of the resources that we had. So I did have a Petzl crevasse kit with me at the time. This is not what my spar kit looks like today. I have tweaked this since then. However, this is what I was carrying at that time period. And so I had a pretzel crevasse kit, had a couple of Pro 6 and some cord and some things to build anchors with. The biggest thing that we did have was training. I had just been to the spar class with NCRC the week beforehand. One of my teammates had EMT training. I had WUFA training. And 3 of the people in our group had OCR training. And one of the people who was in our group was a member of the French rescue team. His specialty was in deobstruction and explosives, which wasn't exactly what we needed at that moment, but he had rescue training that involved hull systems. So he knew what to do too. So amongst the gear that we had, there was the crevasse kit. This microtraction here is a pulley with progress capture built in. So basically, this is a one-piece unit of that pulley with the Prosic as I was showing it earlier. We had a pulley. We had a couple pulleys, actually, a couple of carabiners. And the greatest thing that we had was a lot of rope. So we brought a 300-foot rope to drop the 165-foot pit because that's the length of rope that we owned. We had another rope that was brought into the cave for another drop in the or a climb in the cave, which was 30 feet. But we didn't know that at the time how long that was. So we had brought a 150-foot rope for that other pitch inside the cave. We also had 50 foot of practice rope that was left at the surface, some webbing, 2 more Pro 6 and a pulley. And basically we started a call out when it all happened. This is the drawing of the system that we actually built. So the 300-foot rope was built right here. We had a bomber anchor rigged to 3 trees, and a big carabiner here. Our microtraction was here. I was getting hauled up, and Cody was my rescuer. Cody is a 6-foot tall person. He weighs a lot more than I do, and this is the fastest I have gone back up a pit. So Cody climbed this rope. The 150-foot rope got repurposed. Obviously, 150 foot does not reach the ground, especially after it has been rigged up to the surface going down the pit. So this rope was free dangling, but he was within equilibrium in a position where he could still use it as his safety line. And then Dustin, at the last bit to get me over the lip, had a 3-to-1 system that we piggybacked onto this carabiner, which we had rigged lower for that free hang. This is the poor person's version of the Dragon Hall. We didn't have enough rope to turn this directly into a the very elegant solution that the Dragon Hall is, where Cody could have transitioned over and climbed that. However, Dustin's a strong enough person that he was able to use a 3-to-1 system, which has mechanical advantage. So he's experiencing 1/3 my weight that he has to carry to bring up by pigging on that 3-to-1 system directly onto this. So that edge was transitioned by basically a 3-to-1 system that was pigged on instead. And that's again that picture of me getting hauled out of that cave. So now you guys have a little bit of a background on counterweight hall system or counterweight systems. Are there any questions? No questions?
Hey, Stephanie, this is Chris.
Yeah,
I don't have any questions, but I just wanted to thank you for doing this. I'm not really a caver, but I'm a climber and a rope access person and a fireman. So this has been just informative to me, just in learning these new concepts. So I appreciate you doing this.
cool. Thank you. Appreciate that.
But yeah, if I have questions, I'll contact you. But no, this has been very
Feel free.
informative.
Yeah.
So
And
appreciate you.
anytime that you guys have like a topic that you're interested in caving, I may not know the answer, but I can certainly reach out to people and ask them to like present as part of this series. So give us topics. Well, I appreciate you guys for joining. If there's nothing else, that's really all I had to present. So,
Well, no, thanks again. Very informative.
all right. Thanks, y'all.
Bye.
Thanks,
Have a
Stephanie.
good night. Yep. See yous.